Hello, everyone, and welcome to our lecture today. Um, Let me tell you something important. This is a second recording for from our lecture. So I think we had like 50 people, 53 people yesterday. But we had a technical problem with the recording, so I'm basically doing a second recording from the first half of the lecture. So, unfortunately, yes, I couldn't recover the first half, but I remember what were the questions, so I actually modified the PDF already and also the presentation, right? So I'm including explanations from the topics that people were kind of confused, right? So hopefully this will be a better explanation from the one from yesterday. Okay, so today we will talk about interpolation, lights, and shading. And if you haven't noticed, we already have the extra video from rasterization, basically the explanation on how we can determine the the pixels that are basically corresponding to different portions of each triangle, right? Basically taking information that is in a continuous form into a discrete form. So the learning goals for today is talk about something called bilinear interpolation, barycentric coordinates, which are basically two different ways to interpolate the data, right, that comes from the vertex shader. And we will start talking about lighting. Today we had an introduction to how the light basically behaves on different surfaces. So we will talk about something called bidirectional reflectance distribution function. We will keep talking about these topics about shading models and lighting on our lecture on Friday, and also probably a little bit on Monday. Lighting and shaders, shading models are very complex topic, and we need to talk about many things and textures and maps, but everything is kind of related with lighting and basically what you finally do in the fragment shader. So you don't need to see the extra video from rasterization. If you already saw the video, is perfectly fine, but you don't need to see the video to understand the lecture today. However, yeah, you obviously need to see it, right? So please, if you haven't, go and check the extra video, and we have already also the PDF. Okay, so the final result from the first part of the rasterization, or the rasterization per se, is again taking a triangle that is in continuous form, right? That is basically an object in 3D, and identify which pixels from your image are corresponding to certain portions of your triangle, right? So we already know that those portions are called fragments. So this is what we have, right? So we identify with this algorithm that it's already explained in the extra video. We identify that, for example, this pixel in particular corresponds to this position on the triangle, right? So now the algorithm that we will talk about today, or the problem, is called interpolation, right? So what do we have right now? We have the triangle with its coordinates, right? So we have the coordinates for these positions here. We have we have the 3D coordinate of this fragment in particular, right? We have the coordinate of this portion of this triangle, and remember, this is similar to just throwing an array and basically intersecting array with a triangle, right? And so having that information in terms of coordinates in 3D space, what we now want is we want to compute and interpolate value from other data that we also have. So for the vertex here, these vertices, we can we have obviously the coordinates in 3D coordinates, right? But we also have other information. We can have normals, we can have colors, we can have texture coordinates, or many other stuff, right? So the goal for the interpolation is not to compute the coordinates of this point in particular, right? The point of the fragment. So imagine that we have something like this, right? We have a triangle and we have vertices A, B, C, right? So in each of these vertices, we have the coordinates, of course, but we also have other information, right? So we have normal, color, any other stuff. We have the point P, which represents the fragment, right? Which represents a portion of the triangle that is exactly the same position than a specific pixel, right? So in this case, P, the value that I need to compute from P is not its 3D coordinates. I already have that, right? The problem is that for the point P, I only have the coordinates. I don't have color, I don't have normal, right? So the problem of the interpolation is to compute these other values that are not the coordinates, okay? So when we are talking about that we need to compute the corresponding value of P, by value we mean the interpolated value from any other variable different than the 3D coordinates, right? So in this case, in the following slides, all the formulas and other variables are talking about color, not position. I think yesterday that was probably the most confusing part of the slides, right? Because yeah, at the end it seems that the data is already there, right? So why I am computing P again if I was already knowing where is the position of P, right? So again, I will repeat. I have the positions of A, B, C, and P. I know the position of P. I have its coordinates. What I need to compute is the color of P, right? Which needs to be not red, not blue, not green, but a color that needs to be like a weighted interpolation, right? A weighted combination of all these three colors, right? So imagine, for example, if the point P is closer to the point B, the color of P needs to be more green, right? Rather than blue and green and blue, right? Sorry, blue and red. Because obviously it's closer to P, right? So the color green needs to contribute more to the color of P, okay? So yeah, and the same, right? So in the following formulas, when we talk about ABC, we are not talking about the position of ABC, but the colors, okay? So ABC represent colors, okay? So the first option, the first algorithm that we can use to compute, again, the interpolation of, for example, the color, it's called bilinear interpolation, okay? So with bilinear interpolation, what the first thing we need to do is to compute coordinates. In this case, we are talking about coordinates. To compute coordinates of 2 points, one on the left and one on the right. How do we compute this? Because again, yesterday people were asking if these were just computed randomly, right? So it's not random. Again, we have the position of A, B, C, and we have the position of P. It means that we have X, Y, and Z coordinates. Let's, for now, pretend that we are talking about 2D, okay? So if we are talking about 2D, let's pretend that this is the X coordinate and this is the Y coordinate, right? So you take the Y coordinate of P, which is this line, right? You take the Y coordinate of P, and what you do is you basically compute the intersection of that Y coordinate in particular, the intersection with this line, with the vector AC, and you will get this coordinate, right? The coordinate of PL, not the color yet, but the coordinate, right? So again, PR and PL, PR and L, these points right here, are not coordinates, right? In these formulas here, this PR and this PL, I'm not talking about the coordinates of these guys, I'm talking about the color. Is how am I going to compute the color, right? This greenish color and this kind of purple color. So because it's coordinates, I'm already have it, right? So we need to compute the coordinates first, and those are computed as the intersection of P in the y-axis with each edge, okay? So again, these are not random, and this line is perfectly horizontal because it's just the the y axis from P, okay? So first step, I compute the coordinates of PL and PR, and then I compute its color. So how do I compute the color? The color is computed like this. So basically, you need, once you have this coordinate, you then need to compute these distances, E1 and E2, and D1 and D2, right? Having its coordinate, it's very easy to find these distances. So in order to compute the color from PR, let's talk about PR first. In order to compute this color, where my mouse is, right? I need to somehow, I need to know which color needs to contribute more, right? I have two colors in this line. I have the color of C, which is blue, and I have the color of B, which is green, right? So basically, I just need to take each of those colors and multiply them by a number, right? By a weight, in such a way that the combination of those two weights needs to be equal to 1, right? The combination of both weights needs to be 1. But that way needs to determine how much each color is contributing depending on its distance, right? So in this case in particular, the point B is closer to the point PR, or the coordinates of PR, right? It means that the color green needs to contribute more, okay? So in this case, we will multiply the color B. Remember, B is a color, right? So we multiply the color of B by the ratio determined by distance E2. So this sometimes could be confusing and counterintuitive, like why I'm taking E2, why E2 is referring to B, right? If it's on the opposite side. Well, it's because this one is the one that is closer. So the ratio, the ratio that is larger is the ratio from E2, right? The same for C, right? The color C is further from the coordinate from PR. So this guy needs to contribute less. So I need to multiply this guy using the ratio that is shorter. In this case, the shorter distance, that is E2, right? So this is what you do. For each ratio, you basically just compute this distance. For example, in this case, for B, you compute the distance E2, which is the largest one, right? And just divide it by the entire distance, and you get the ratio from E2, and you multiply that times the color of B. So it needs to be, so this means that color green will contribute more, right? So this will be the contribution of the color green plus the contribution of the color blue, and you get PR, which is basically this color, right? This is like turquoise or something like that. Okay, so the same happens here, right? So you compute distance D1, distance D2. D2 needs to refer to the color of A, and D1 needs to refer to the color C, right? So basically, when you're doing this linear interpolation, the ratio that you multiply, the ratio you take to multiply each vertex is basically the ratio that is on the opposite side, right? So we don't take the ratio that is closer to this point, but the one that is on the opposite side. Okay, so that is how you compute colors PR and PL, right? These colors right here. And this formula is only a linear interpolation, right? So the reason this method is called bilinear interpolation is that because we will basically combine two linear interpolations, right? So this is called bilinear interpolation. So we have one linear interpolation to get this color, another linear interpolation to get now this color, and now the next step is to compute now the final color for P, right? So we now get the distance C1 and C2. So remember, we have the coordinates of PL, we have the coordinates from PR. So we know now in the x-axis, we now have this distance, right? C1 and C2. And we basically apply the same formula. We take the color of PL and we multiply it by the ratio from the opposite distance. We take the color of PR and we multiply by the ratio of the opposite distance, right? And we sum those things and we will get to the color of P. I'm not actually drawing the color of P. I probably forget to do that. Obviously, the point P is not black at the end, right? It will be basically a combination from purple and this color here, right? So this is one option, right? One option to compute the linear interpolation. And remember, why do we need to do this? Because this represents a fragment, right? So if we have different colors on, if we have colors on these vertices, different colors on each vertex, the color of the fragment needs to be a combination of the colors of its vertices, right? Yeah, so I think Yes, I think those were basically the questions people had yesterday. Okay, so now we can do it with another option. This is just another algorithm. So by linear interpolation, it's one possible algorithm. This is another algorithm called barycentric coordinates, and this is in particular very useful. It has a very interesting geometric intuition and is very useful in ray tracing. You will see later when we talk about ray tracing. Okay, so again, this is another option. Basically, you can compute the color of P, right? Taking the colors A, B, and C and just multiply them by some weights. It's literally, I mean, mathematically it's different, right? But in the end, it is equivalent to bilinear coordinates, right? Because we are multiplying each color by some weight, right? To get a new color. Basically, that's it. So alpha, beta, and gamma are basically these weights. And the way it is computed is as the following. So basically, the barycentric coordinates, the geometric intuition behind this is that it's just a relation between areas. So we will compute different areas. So the first area that we need to compute is AT, which is basically the entire area from the triangle. Okay, so AT is, you already probably remember this. In order to compute the area of a triangle, we just need to take half of the magnitude of the cross product of two of its vectors, right? And remember, we don't normalize these vectors, right? So here in particular, we don't need to normalize them, right? So we have the vector AB, which is this vector, and we have the vector AC, which is this vector. We take the cross product, we take its magnitude, and we multiply by half. And that is basically the area of AT. Yeah, I think everybody at this point should remember this, right? So then the next step, that is the first step, right? Taking that area. The next step is to pretend that you split the triangle into three little triangles with lines that are basically connecting A, B, and C with the point P, right? So imagine that you are basically connecting point P with those lines, and that gives us three little triangles, and we will compute the areas from those triangles, right? So the first area is the area that corresponds to the point A, and that will be the area that is on the opposite side of A, right? So area AA, right, is the one that is opposite to this point, and is the same. It's just half of the magnitude of the cross product between PB, which is this vector, and PC, which is this vector, right? So this is AA. I think you get the idea. Now we have to compute AB, which is the opposite area from the point P, and again half of the magnitude of PA and PC in this case. And then we compute the third area, well, sorry, in this case the fourth area, which is AC, the one that is corresponding to the point C, and that is the opposite to the point A, to the point C, right? Exactly the same formulas. We just change which vectors we are using, right? So now that we have these areas, right, the way we compute the actual weights is by just taking a ratio between those areas, right? So the ratio or the weight alpha is going to be the area AA over AT, right? So this area over the entire area, right? And the same for each weight, right? So the beauty of the barycentric coordinates, so one of the beauties of the barycentric coordinates is that these ratios need to always sum to 1 when the point P is inside the triangle. So let me show you an example, graphical example of this. Okay, so we have an example here, like an interactive example in 3 to the max. So we have 3 points, right? Red, green, and blue. It's very similar. And we have a point that is represented by this sphere. And basically the code is computing the barycentric coordinates for this guy. So basically these are the barycentric coordinates. So this is alpha, this is beta, and this is gamma. Beta or beta? I don't remember how to pronounce it. I think it's beta. Beta and gamma. And again, if the point is inside the triangle, the sum of these guys will be 1, right? But here I have something to tell you. Remember that you always when we compute value, when we are dealing with floating values, which is very, very common in computer graphics, right? We always deal with floating numbers. You need to take into account that it will be almost impossible to get exactly 1.0, right? So this value here is in my code, right? I'm forcing this guy to be 1.0. So whenever you want to compare, for example, I don't know, when you're, for example, comparing a dot product with some value, and maybe you want to know if two vectors are the same, right? And you're taking the dot product and you expect the dot product to be 0, right? If they are 90 degrees, for example, and you literally in your code you say, oh, if this value is equal to 0.0, that will probably never happen, right? So in computer graphics, something that is useful is you usually have a very tiny value that we usually call it epsilon, right? So you have an epsilon value that is maybe 0.00001 or something like that, and so you basically compare, right? If the difference between your value, sorry, in this case, for example, to compare if the sum of these barycentric coordinates, instead of just literally computing its sum, if its sum is equal to 1.0, you can say if the difference between its sum and 1.0 is less than this epsilon value, right? So yeah, this is just like a quick tip in terms of implementing stuff, because this is a very common mistake in computer graphics. Okay, so again, the sum of these guys, right, needs to be equal to 1 if the point is inside the triangle. And this is basically the interpolated color. So if I take this sphere right here and I move it closer to the point red, right, it will be more red, right? And you can see here that the coordinate, the barycentric coordinate, by the way, yes, I mean, those weights are the ones, those weights are the actual barycentric coordinates, right? Because it's like x, y, and z, right? But from a different space. So it's x, y, and z with respect to a triangle, right? So that's why we call it coordinates. But those are just weights, right? So basically you can see that the weight from the color red is larger, right? It's almost 1. It's 0.92 blah, 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 right? So it basically means that red is contributing more, right? It makes sense, right? Because its area, its opposite area, is way larger, and this guy is closer to the color red. So the color red needs to contribute more, of course. And the same happens, right? If I take this guy and I put it very close to the point blue, its coordinate, right, or its weight will be larger, of course, right? So in this case, now this is the one from blue, and it's obviously larger, and now the color is very close to be blue, right? So it's bluish, right? Because the color blue is contributing more. So this is how the barycentric coordinates work. And you will probably wonder why it is important to know the sum of these weights, right? If the sum of these weights is equal to 1. Well, because, and again, this is in particular very interesting we deal with ray tracing. When we compute ray tracing, for example, what we do is basically we throw a ray that hits this triangle, right? So if we throw the ray and hits the triangle, the way we compute it is we basically take the ray as a vector and we compute the intersection from that vector, or from that line, the line from the ray, and we compute its intersection with the plane from the triangle, right? Remember, a triangle is always representing a plane, or a triangle is always living in a 2D plane. Right? So we first compute the intersection between that ray with the plane, and once you have that coordinates, right, those coordinates of the intersection with the plane, you compute the barycentric coordinates of that point, the projected point, with respect to the triangle. And if those barycentric coordinates are larger than 1, it means that that point is not inside the triangle. If it's exactly 1, it means, or not exactly 1, but remember, you can use this epsilon trick, right? But if you realize that the barycentric coordinates tells you that that point is inside the triangle, it means that you are literally hitting that triangle in that position, and then you can use it to compute color, right? That is what you usually do in ray tracing. So if I take this guy outside, right, it's very intuitive to understand what is happening here, right? And someone yesterday was wondering, well, what happened if, because we are dealing here with dot products, right? And they were asking if we could have like negative areas and things like that. Well, geometrically speaking, there is no such thing as a negative area, right? Geometrically speaking, at least, right? There's no such thing as a negative area or a negative volume, right? We're not dealing with weird non-Euclidean stuff, right? So there is no negative area. So what is happening here is basically now the sum of these three areas is obviously larger than the original area from the triangle. So of course the sum of these weights is going to be larger than 1, right? So in this case, this point is obviously outside the triangle, and it will be larger than 1. So if it's inside the triangle, it's always 1. If it's outside, it's always larger than 1. And someone yesterday was wondering what happens with the color. What happens in this case, in which the point is outside the triangle? What happens with the color? And I was telling them that it was very hard for me to predict what will happen, right? Because if it's inside, it's very easy to imagine what is happening and imagine which color is contributing more. If it's outside, it's a bit harder to imagine what color is contributing more, right? So in this case, for example, the one that is contributing more is in this case green. However, the color is not greenish, right? Sorry, yeah. So I also tell them to the students yesterday that it depends on how your algorithm works. So if we are talking about colors here, the value from this color channel. So remember, when you're talking about color, you basically have RGB and alpha, right? So those numbers are usually called channels, right? So you have the red channel, the green channel, and the blue channel, and the alpha channel, of course. So depending of the system, in some systems, the color is defined by values that go from 0 to 1. And in other systems, the color value is defined as from 0 to 255, right? So the range, depending on the system, could be different, either from 0 to 255 or 0 to 1. The thing is, usually when you're coding, right, if you're coding something related with color, if someone is creating a code related with color, there are two ways of dealing with numbers that are larger than those ranges, right? So if the value of a specific channel, let's say the value of the channel red is larger than 1, and I'm using the range from 0 to 1, there are two ways to deal with that number, right? You either cut the number, right, and just make it 1. If it's larger than 1, you just make it 1 and it's full red. Or you like take the next cycle, right? So you basically take the difference between 1, right, and that value that you have that is larger than 1, and you basically take that value as the value from your channel, right? So it means that if the color is 1.2, the actual value will be 0.2, right? So instead of being full red, it will be just a little bit of red, right? I'm not saying that is correct. Actually, I think that the correct way is just clamping the value into 1, right, or into like the upper value from your range. But I've seen people doing that. I've worked with software that apparently works like that. Works by just like taking the difference, right, between the integer. And by the way, I think yesterday I said clap instead of clamp. Yeah, so sorry about that. Sometimes I had to read also the chat to see where were the relevant questions, And yes, yeah, guys, yeah, sorry, my English sometimes is very bad. Okay, so yeah, so again, it depends. It depends on how you implement your algorithm. And so, for example, here I really don't I didn't code that part. I'm literally just sending the numbers to trees to the max. So trees to the max is dealing with those. I really don't remember what trees to the max does with colors. I guess because trees to the max is a very sophisticated tool for computer graphics. I guess they're probably clamping the values, right? And if the value is larger than, in this case, 255, because the range in trees to the max is from 0 to 255. I guess the value is just the upper value, right? Yeah, but again, it's difficult to predict. I think we put the guy here yesterday, and it turns out that it was brown, right? So I was probably thinking that maybe it will still be bluish, right? Because the color blue is closer. However, it turns out that it's brown, right? So the red channel is starting to contribute, and yeah, it turns out it's brown. Okay, good. So let's continue here. Okay, so this is basically how you compute the barycentric coordinates, and if you do that for all the pixels, right? So if you compute barycentric coordinates, if you interpolate the color using barycentric coordinates for all the pixels that are basically inside this triangle, you will end up with something like this, right? And people was saying, oh, this is the video game triangle. Yeah, this is obviously when you start to learn about video games, this is something that you sometimes see, right? It's basically that. It's the graphical version of this interpolation, right? So we are seeing here is that every pixel here is being interpolated among these three colors, right? Red, green, and blue. And this is the way it is computed. So again, all these examples, we're talking about colors, right? But you can interpolate any data you want, right? It's not only colors. So you use exactly the same, for example, to interpolate normals, right? And we already talked about that. So if you have a surface like this, right, you basically either have the same normal for each triangle or each face, or you compute a normal for each vertex and you interpolate the normal values, right, using barycentric coordinates, and you will have this beautiful surface. So this is basically how interpolation works. I think I had my notes here, and I think I've covered all the questions that were asked yesterday. Yes, I think I'm not forgetting anything. Okay, so from here, the next part of the video is the part that was recorded, right? So I only lost the first part. So the next part, it is the original recording. And yeah, again, sorry about this. Obviously, if you're probably seeing this video very probably on Thursday, right? And because I had to record this very late. Okay, good. So let's talk about now lighting, right? So basically what we were discussing now is how, or the algorithms that we basically need to implement to define how different materials react to the lighting, right? Either the angle from the light, the intensity of the light, or also the actual structure from the material, right? So let's see, for example, this picture, right? So we have two different surfaces right here. One is very shiny, right? It's almost like acting as a mirror. It's obviously not a mirror, right? But it's acting as a mirror. But in the other image, it seems that it's basically the same surface, but the surface seems more like blurry, right? Or the reflection seems more blurry. So this is basically regarding or related, sorry, with the microscopic structure from the materials, right? And they're super sophisticated shading models. They're actually trying to mimic like very realistic microstructures of materials. I think I think Dinesh is even like working on that. But usually in shading models, we usually try to like mimic that effect, right? So let's see this two different surfaces, right? So what is happening here is, imagine that you have a surface that is completely flat, and the orange arrows are basically the light rays, right? It's basically the light coming from your light source. If this is perfectly planar, it means that all your lights, or your light rays, right? It will be reflecting. It will be reflected to exactly the same direction, right? It means that the reflection on your surface will be super crisp, right? As a mirror, right? A mirror is basically an object whose microstructure is super flat, right? So if it's not completely flat, right? If it has certain like hills and valleys, right? Like something like this. What will happen is basically the light will be bouncing in different directions, right? And as the surface of this object, right, is more like rough, right, not completely flat, basically the light will bounce to whatever direction you want, right? So that is basically why you can see the reflection. In this case in particular, you can see that the reflection is more blurry, right? So this is basically what you do when you are like kind of computing the values or different materials, and you will see how we do that, right? So let's first talk about a certain type of surfaces called Lambertian surfaces. And this type of materials, basically what happened with them is that they appear brighter, or they reflect more light when the light hits from above, right? So basically when light is hitting at a particular direction to the surface, or you can say that when light is basically hitting in the same direction or the opposite direction of the normal of the surface. And they appear dimmer when light hits them from the grazing angle, basically when the light is hitting on an angle that is orthogonal to the normal, right? And if you study how different materials actually behave and how much light is reflected depending on the angle of the light, right, with respect to the normal, you will see that they have a very weird different materials. They have some weird distribution, right? In this case, it will be similar to this. In this case, is PVC plastic. This is a very simple example of plastic. PVC plastic is just a certain type of plastic, very similar to the surface of your laptop, for example. Your laptop is probably made of ABS plastic, but it's basically very similar in terms of how they behave with the lighting, right? So imagine that this vector here, right, is the direction in which the lighting is bouncing, right, on this surface, right? So this surface is this plane. This is the normal of the surface. And this vector right here is basically the direction of the light, right? So depending on the direction of the light and how it bounces, you will obviously get more light reflected, more photons reflected on the exact direction that is basically the reflected version from the light with respect to the normal, right? And as soon as you move into different vectors or different directions, the amount of light that is reflected will be obviously less, right? So this model, or basically that shape, or how if different materials basically distribute the light that is reflected, it's called bidirectional reflectance distribution function. And again, different materials have different BRDF, right? And again, this could be super complicated, super sophisticated. There are thousands of papers on SIGGRAPH, on CBPR, or whatever conference you want, talking about these topics and rendering, and it could be super complicated or super simple if you create like clever shading models. That is what we are going to see right now. Okay, so let's keep talking about Lambertian surfaces. So the reason why, right, why a surface is basically bouncing more light when light is coming from above is because how those photons are basically distributed on the surface, right? So if for example, in this case, the same amount of photons are hitting this surface exactly on opposite direction of the normal, basically a certain amount of photons are reflected on this distance here, right? However, if basically the light is now in a different angle, right, the distance in which these photons are distributed will be larger, right? So now they will bounce from a larger distance, which means that the color or the amount of photons per square meter, right, will be less, right, because they're basically distributed in a larger area. So basically, in the end, is the amount of light that is basically reflected in a surface is proportion to the cosine of theta, right? So basically, the dot product between the light, right, the light direction, and the normal of the surface. And this is why we need surfaces when we are computing our renders, right? And this is why we need to store that information in the vertex shader and get that information already interpolated for each fragment, right? We need those normals, right? Okay, so there are different approaches in computer graphics to render stuff. So this is the most basic one, the flat shading, in which in this case you basically compute you basically compute the light per triangle, right? So in this case, for example, you could even not care about the fragment shader because you don't even need interpolated values, right? So you compute a single normal per triangle, and you basically assign to every fragment on those triangles, you basically assign the same color, right? So you can get something like this, right? And again, I mean, this is exactly the case when we were talking about before, the case when your normals are not interpolated, right? Because we are using basically the same normal for the entire flat shape that is represented by each triangle, right? So this is called flat shading, right? It's one time per triangle. There is another way to compute lighting, which is, okay, I will get different normals per vertex. So it is a different, right? Because in the previous one, you have a normal vector for each triangle. In this case, you have a normal vector per vertex. So imagine, for example, that this is a surface. This is one triangle. This is the surface of one triangle. And imagine that there's another triangle here. I hope you can see my mouse. There's another triangle here, and there's another triangle here. So basically what happens when you compute the normals of a vertex is you compute the normals of all the triangles that are neighbors of this vertex in particular, and then you just take the average, right? You take the average of those normals, you get a new vector, you normalize that vector, and now that vector is the normal from this vertex in particular. So Gouraud shading is a shading model in which instead of using a single normal per triangle, we use the one from the normals, but we compute the color of the object on the vertex, right? Not on the fragment shade, not on the fragments. So for example, you can actually compute this directly on the fragment shader. It sounds weird, right? Because we usually understand that what you usually compute on the vertex shader is only the position of the vertex, right? And then you just pass information, right, with uniform variables or variant variables. You pass information to the fragment shader, and you actually compute the color on the fragment shader. Well, in this case in particular, it's a bit different. You actually decide the color of the surface at the vertex level, and you can compute it in the vertex shader. And that color, you can store that color as a variant variable. So basically what will happen is you will get a color for this vertex and a color for this vertex, and the color will be interpolated using barycentric coordinates. It's exactly the example that I was showing you when we were computing barycentric coordinates, right? The color is computed not at the fragment level. It's computed at vertex level, and then it's just interpolated for the fragments, right? So this is what you will see, basically. There's another shading model, or another family of shading models called Phong shading. This is different. In this case, what you interpolate is not the color of the vertices, but the normal of the vertices, right? So you get, again, you get a normal for each vertex, but instead of computing the color on the vertex shader, you just use the normal, right? And you pass the normal to the fragment shader. So what you obtain, what you get in the fragment shader is not yet the color of each fragment, but only the normal. And then you use the position of your light and the angle and the material properties and many other stuff, and you compute the final color on the fragment shader. And I need to finish right now because it's already 3:53. Okay, so we will continue with these topics on our next lecture. As I told you, lighting is very large, right? So we need to talk about this. This was only an introduction. So basically for today we had this and another break, right? And a couple of more slides, but we will talk about that on our next lecture. Okay. Any other questions? I think we have maybe like 2 minutes for one last question. Professor, okay, someone is asking, is barycentric coordinates only used to interpolate vertex color? No, barycentric coordinates, you can use barycentric coordinates to interpolate any information you want. Again, remember at the vertex level, you can have a lot of information stored in each vertex. So you can compute, or you can store maybe the color of the vertex, a texture coordinate, you can compute the normal, you can compute a crazy value that maybe you will use later to make a crazy effect on the vertex shader. You can get a lot of information on each vertex, and then you use barycentric coordinates to basically interpolate all those, right? Yeah, you can have thousand different values interpolated with barycentric coordinates, not only color. Okay, good. Thank you, everybody. I will take a little bit more time today to upload this video, right? Because, you know, I made this horrible mistake of not recording the first part. So I will record the first part, and I will try to mention your questions. So hopefully I will remember all the questions. And thank you so much. And please go check the extra video. Bye.